right? So yeah, we see very smaller updates in your weights if your weights are very small, right? And this typically leads to a problem called as vanishing gradient. Okay, and how do we solve this vanishing gradient problem is you have to scale your weights appropriately, right? So typically, um, the way you choose is say y is some summation of, let's say, w times x. So this is typical of neural network, right? So the goal here is to maintain the variance of your output is same as the variance of your input. Variance of your input. Okay, so assume all x have similar variance, right? So if you see that if you want to maintain this thing, you would want to scale your weights with say 1 over square root of your size of the input, right? If the weights have unit variance, right? When you have activation such as ReLU, you have to do this by square root of 2. Right? This is a proper popular initialization called as he. He is named after the author of this work. Okay. Um, and another quick overview of this thing is activations. Uh, yeah, let's see. Can see the questions. Yeah, which of the following best describes the concept of saturation in deep learning? Right, the activation function output approaches either 0 or 1, and the gradient is close to 0. So basically, you hit a saturation in any DL models once the gradients are close to 0, and no matter what is the cause for it. Because you are not learning anything. Now, which of the following method can help avoid saturation in deep learning? Right? By using a different activation function, that is fine. And increasing model complexity is not the solution. And that is to minimize uh, that is to improve the high bias problem, just as we discussed now. Increasing the learning rate, no, that also doesn't help. I mean, increasing learning rate even worse the case because you may make pretty large updates and hit the saturations within the activations, right? So basically, for example, if you take sigmoid activations, right? It saturates when the input is high, right? And also because of its what should I say? Even if the you see the backprop of the sigmoid, it is multiplication of sigma times 1 minus sigma. Even there, it it assists in your this thing vanishing gradients thing, right? So typically you change your activation and see, um, just to avoid saturation problems. Again, what is the role? What is the following? Which of the following is true, and about the role of the unsupervised pre-training in deep learning? Right. Basically, what is unsupervised pre-training in deep learning is you initialize not randomly, but you initialize some model that is pre-trained on some other data, and you customize this model for your own task, right? So yeah, so typically pre-train using the pre-trained model helps a lot for your faster convergence, and it does give better performance because your pre-trained model would have already seen a lot of more complicated data, and your task may be simpler than that. So that's the typical advantages of using pre-trained models in deep learning, and this is widespread. Typically, people don't train from scratch in deep learning because that is very costly. You just train a good pre-trained model and fine tune the last few layers on your data set. That's it. I think we just discussed the advantages of this thing. What is the following advantages of unsupervised pre-training in deep learning? Pre-trained models converge faster because it has already seen that data. It improves the accuracy of the model because it might have already seen more complicated data. Now, why it helps reducing overfitting? I mean, it may not be always true, but yeah. Yeah, what is the main cause of dead ReLU problem in deep learning? Okay, so this discuss this lead this needs some discussion, right? What is the typical structure of your this thing? Affine, and the affine followed by your ReLU, affine followed by ReLU, and affine followed by ReLU, and so on. The problem happens is if, say, you learned by FN, I mean this W express B. If you have learned your weights W and B such that after adding B, all the inputs are negative, let's say -1, -2, and so on. Understand. What comes to ReLU then? This is all zeros, basically. right? So this weight will never get updated. And just imagine if that happens for many, many more layers, right? Then you are you will never learn, right? In such a case. So this problem is called as dead review. One simple solution is this is ReLU, right? I mean this is zero and then negative and it is give the same pass the same input as output and it is positive. So one typical solution is to have a leaky layer, a leaky ReLU. That is something like this. A very small output when input is negative. So that is y is equal to you can say 0.0001 times x if x is negative. That's one of the solution. Okay, so that's the main cause, high negative bias. Yeah, again, right? How can you tell that your network is suffering from dead ready problem? If you see large number of neurons that are giving you a zero output, right? That is a typical indicator of the problem that you are having is a dead ready problem. Okay, that's very simple. Like, what's the mathematical expression of ReLU is a max of 0, comma x. Right? If x is positive, you give the positive value as output. If x is negative, 0 is the maximum. So you give 0. That's what is the main cause of symmetry breaking problem in deep learning? Symmetry breaking problem. Right? It's a equal initialization weights. I mean, so I think last week I told, right? If you initialize all of them to 0 weights, it will not learn. But what I mean, and now I say that all weights are initialized equally, not 0. What is the problem? A simple network W1, some activation, say really another another layer W2, say some activation, and you have something, some loss. The point is W1 is initialized to say all one vector, all ones. And W2 is also initialized to all say minus ones or something. And say W3 is also initialized likewise. Ones or minus ones or two or minus two or whatever. And so on. What is the problem? Now this is not same as you have all zeros as input, right? What is the problem in this case? This is also um, this also doesn't break the symmetry, but what is the cause? Why do you think it's a problem? So thing is, all weights behave in a same manner here in this case. So basically, this is as good as having a single neuron, not a matrix of weights. Just as good as having a single neuron because all the points in this your matrix behave the same way. I mean, they all get updated in same direction. right? So that's the problem, because you're saying like you're initializing with these big matrices, but the point is that it is effectively doing as what a single neuron does, right? So that's not what you want. Okay, so that's the problem. Okay, and yeah, what's the purpose of batch normalization in deep learning? Any idea on this? I didn't discuss this just before we start Q&A. Yeah, but I'll explain you in bit more detail why this was introduced and what is the potential reason of this helping. Okay, any answer? So basically, what happens is, I think let's see what is the time. I think. Okay, in batch normalization, what happens is you center your data mean and variance such that what you get is every activation at every input to layer, you should have a zero mean and unit variance for each neuron, and that you make it trainable. So here you train with this gamma, some parameter, right? This 10th question needs bit more detail. So let's give detail and call it a day. Okay. So what is a batch normalization, right? I'll take a single neural network. This is W, and this is A, and so Y. So, so basically, this is something like fine. After this, multiply your weights. What we do is we compute the mean of all the examples. Say this is for one example you got. So yi you got y1, I goes from 1 to b. Let's say batch size is b. So what we do is 1 over b, I is equal to 1 to b. Right? This is your mean y bar. Similarly, compute variance. Typically, you can do b minus 1. That's unbiased estimate. Okay, so this is variance of y. Okay, so then what do you do to this? How do you transform this y is transformed to this something like this? Okay, y minus y bar divided by your square root of this variance sigma square y. you add some small quantity such that if this is zero, it doesn't blow up to infinity. It's a sigma square one. And this you add with some beta times this guy plus gamma. So this is scale and this is shift. Yeah. Okay. So typically what happens in this thing is typically input you normalize and the distribution in the inputs. So in the space, it looks like this. And this is activations, let us say. And as it keeps passing through ReLU, it gets skewed, right? So more and more will have towards zeros, right? So the problem is what they say is here weights are weight here the weights function is acting on x which is distributed something normal. For W2 it is not the case because there are more zeros and they really knocks off most of them. So your distribution is changing with respect to W2. This is called as covariate shift. So actual batch norm was introduced to address this covariate shift. Now, yeah, I mean, this was fine. I mean, people started using it, but it was not clear why it was giving the results. So the people conducted some experiments. So one popular experiment was this. So one, two, and three. So this is a network without batch norm, and this is network with batch norm, and this is a network which has batch norm, but it adds some noise. So basically here, I mean, because so it has covariate shift, right? So internal covariate shift it has, and this says that internal covariate shift is reduced. That's why batch norm helps. But in their experiments, what they do was they they artificially introduce covariate shift and they use batch norm with that, right? And they still see very good results with that, right? So batch norm is doing something more than what it was uh, ideally introduced for, right? So basically, what it does is it typically the claim is um, it smooths the loss surface. That's why it is able to perform better. Right? So I mean, yeah, the real reason why it does the good job is still um, not well understood. To be frank, right? So if you find an option of internal covariate shift, just go with that because for that reason it was originally introduced. And actually, why it works is still something we don't understand fully, to the best of my knowledge. Okay, so with that background, um, let's see what was this thing. What is the purpose of batch norm in deep learning, right? It's just to ensure the distribution of the inputs at different layers doesn't change. That's all. Okay. Any more questions? Let's stop the recording.
We now discuss why batch one was introduced, and actually it is introduced to solve a covariance of problem. To be specific, it is introduced to solve internal covariance of problem that is observed in the middle layers of the neuron. So what is covariance shift in deep learning? So covariance shift refers to a change in the distribution of the input data to an NEML model. In the context of deep learning, covariance shifts specifically refers to changes in the distribution of the input data to layers of the neural network being trained. So this happens because of the choice of activation functions, typically using neural networks. So value is the most popular activation function, and it is not symmetric about so it allows only positive activations to pass and negative makes zero. So this leads to a different distribution across the layers of the neural. So what is a distribution shift is the distribution of input data vary across different subsets of the data. This can happen due to various factors such as changing variations in data collection, possible difference in net characteristics of the different data sets. So what is the impact of training the distribution shift or covariance shift has or have is covariance shift can have significant impact on the training process of ML models, including the deep neural networks. When the distribution of the input data with the layers of the neural network changes during the training, it can lead to very slow convergence, decreased performance, and difficulties in generalizing the new data. So, slow convergence means takes very long time to go to the minimum. And difficulties in generalizing new data is performs inferior on the unseen data source. So what is the impact on the training this can have, as we have discussed? And specifically when we have this internal correlate shift. So in the context of BLA, internal correlate shift refers to changes in the distribution of the activations within the layers of the neural network during the training. As the parameters of the networks are updated, distributions of the activations within each layer may change, leading to intercoding shift. So, what kind of challenges that we typically encounter due to this internal covariate shift is a very mm, slow convergence, that is, change in input distribution can slow down the convergence of optimization algorithm that requires longer training times. So we need many epochs for the gradient descent or the stochastic gradient descent algorithm to converge. Performance degradation correlation can lead to a suboptimal performance of the model as it may struggle to adapt to changing input distribution. Generalization difficulties. Models trained on the data with covariate shift and generalizing to new unseen data with different limits. So this generalization implies that um, model is not able to perform well on the unseen data. So to address these problems happening due to the internal covariate shift, the batch normalization technique was introduced in people. The batch normalization addresses the internal covariate shift by normalizing the inputs at each layer. Specifically, it normalizes the activations of each layer by subtracting the mean and dividing the standard deviation of the mini batch. So we batch statistics, giving a training for each mini batch of the data. Batch normalization computes the mean and standard deviation of the activations along each feature dimension. These statistics are then used to normalize the activations of the mini batch. And the statistics are, it also stores buffers, running mean and running mean buffers across the training set so that it can be used in the test time for the inference. So the along with this normalization of each layer, Basham also introduces two parameters, the additional parameters called scale and shift parameters. So These parameters are introduced to allow more flexibility while learning the model. There are only two parameters, it is scale parameter and shift parameter, and the size of this parameter is same as the size of the number of neurons that wait. What are the benefits of using batch normalization? It essentially introduced to address the internal covariate shape, which is the changing of the distribution of the activations in, across the middle layers of the neuron. So by normalizing the mean and normalizing the activations by centering the mean and making it variance across all the layers, we reduce the internal covariate shift. And this allows to speed up the training and by actually allowing it to use higher livelihood and thus enabling a faster convergence. Improve stability. So by normalizing activation, batch normalization helps stabilize the entire training process, making it less sensitive to the choice of hyperparameters such as learning rate, batch size, etc. And batch norm is very sensitive to batch size for people. And to get reliable statistics of batch, we have to use a larger batch size. Batch norm won't work if we use a batch size of one. And it also introduces uh, polarization in some way. Batch norm acts as a form of regularized by adding noise to activations through minibatch statistics. This reduces overfitting and improves the generalization. Gradient batch norm also helps alleviate the vanishing gradient problem by ensuring the activations are within a range which facilitates better gradient flow during the back propagation. Finally, batch norm is a kind of feature that operates differently when training the model and differently when we are using the model for inference. So typically the key components that are different while training and during the inference is the computation of running mean and variance. So during the training, this running mean and variance buffers are keep updated in the batch. During the inference, these buffers are frozen and the training time updated buffers are used during the test to do the inference.